Hey guys, we are going to wrap up this little mini redox unit by balancing redox reactions using the half reaction method. We're just focusing on this occurring in neutral solutions. You will see out there that you can balance redox reactions in acidic and basic solutions, and those have a whole extra set of steps that you have to work through. But for right now, we're just going to focus on the neutral ones. So I already went ahead and assigned oxidation numbers to all the elements in the reaction, which after the last 2 days you should have a pretty good handle on. If not, make sure you go back to the first lesson and review how to assign oxidation numbers and the general guidelines you can use. So once you assign them all to the reactions, you're looking for changes in oxidation number. So for this, I would be looking at the fact that I have sulfur, okay, going from a -2 to an oxidation number of 0. That's really important, something that students forget. Remember, if you have something that is uncombined, the oxidation number is going to be 0. And then I also can see that I have nitrogen going from +5 to +4. Okay, based on their changes in oxidation numbers, that's going to help me identify which one is getting oxidized and which one's getting reduced. So my oxidized element is going to be sulfur, going from -2 to 0 because it's indicating a loss of electrons. Remember, oxidation is loss, so that's your oil rig. All right, so it's going from S2- to S0. So with this change in oxidation numbers, it is a loss of 2 electrons. It's going to transfer 2 electrons from that sulfur to the other species. So just like when we talk about exothermic reactions where you're losing energy and energy is written on the product side, on the right-hand side, the same thing is going to happen with our electrons. So we're going to be showing that this is giving off or releasing 2 electrons. Okay, nitrogen in that case is our species undergoing reduction, so that's reduction is a gain of electrons. So because it's gaining electrons, I'm going to leave space for it on the left-hand side or the reactant side. So nitrogen here is going to be going from +5. I'm going to leave space, and then we're seeing it change to nitrogen with a +4. Okay, I can see by that change in oxidation numbers and create a number line for yourself if you need to. It's just the addition of 1 electron in order to make that change. So I have 1 electron that's being gained here. Okay, so that would be our half reactions for oxidation reduction based on that change of oxidation numbers. The next step is to make sure that in any oxidation reduction reaction, the amount of electrons lost has to be equal to the amount of electrons gained. So I'm going to balance these, focusing in on those electrons. So in my oxidation half reaction, I have 2 electrons lost, and in my reduction, I have 1 electron gained. I can get both of these to 2 electrons. That would involve me just multiplying the oxidation half reaction by 1 and the reduction half reaction by 2. Now, most of you guys can probably from here, after you see me write out the next set of steps, you could jump up and leave out this next part, but I think it's important for you to see and understand where this is going to come from. So here I'm just going to rewrite this after you think about, like, multiplying this across. And then I usually like at this point to line up those arrows. So this would be 2n + 5 plus 2 electrons would be 2n + 4. Okay, which should make sense. If 1 mole of electrons, or 1 mole of nitrogen plus 5 atoms are gaining an electron, 1 mole of it, then if I have 2 moles, it's going to be 2 moles of electrons. So that relationship is held constant. So from there, I'm going to cross out my 2 electrons. So I would have 2n + 5 plus 1 S0. Oh, sorry, -2. 1 S0 over here, plus 2n + 4. Okay, so then in this next part, and let me see if I can switch colors here for a second. I'm then going to look at using these numbers for my balanced net ionic equation for my half reactions as coefficients up above. So when I look at 2n + 5, okay, as long as there's only one place where that shows up here, okay, I'm going to fill that in. So I'm going to initially just underline this here, and then I'm going to fill in it and 2 there based on its coefficient. When I underline it like that, I'm locking that in. That has to be 2 based on that exchange of electrons. If I look at S2-, I only have 1 space where that is up here. So it has a 1, so this must have a coefficient of 1. S with a 0 oxidation number, this is the only place up here that you have it, so I can fill in its coefficient, which has to be a 1. And then finally, coefficient of 2 in front of n plus 4. This is my only place where I have n plus 4. Okay, so I can fill in a 2 there. Okay, those are locked in, which is why I like to underline them, because as long as you wrote your half reactions correctly and you balanced the electrons correctly, those are locked in. And then from there, it's just a matter of balancing everything else normally how you would. If you focus in on, say, the oxygens, you have 6 oxygens over on the reactant side. I already have 4 on the product side, so I need 2 more, so I'm going to put a coefficient of 2. Okay, also if I check hydrogens, that balances out. I have 4 hydrogens. If I add them up on the product side, and then H2O, this is the only place I have hydrogen, so 2 times 2 is 4. So that one is all set. Okay, I'm going to actually have you skip down to 5 because there's 2 things in number 5 that I want to show you, and then on your own you should be trying out 2, 3, and 4. So on number 5 down here again, I've assigned all the oxidation numbers. You'll see I2, it's diatomic, but it's uncombined, so it has that oxidation number of 0, and you can see everything else is pretty straightforward. So just make sure though, practice those on your own if you need to, and then come back to the video. So if I go through looking for what is changing oxidation numbers here, I'm going to see that my chromium is going from +6 to +3. Okay, and then I also can see where iodine, some of them, is going to be going from -1 to 0. Not all of them, and that's going to be important later on, but some of them are. So then I'm going to work through my figuring out what's getting oxidized and what is getting reduced. So in this case, my oxidation half reaction is occurring with some of the iodine atoms. So the ones that are going from -1 to 0 are doing that through a loss of electrons. So this is where a couple of things are going to occur. So I have I, -1. Okay, this is going to be my oxidation one, so my electrons are going to be on the product side because it is losing those. If you have a 2 here, that's going to affect your number of electrons and your balancing and everything else. So I'm going to include that subscript of 2 here, and then that has an oxidation number of 0. Before I do anything with electrons, I'm going to first balance out my number of atoms, so I'll put a 2 right there. So for each iodine atom going from -1 to 0, that's 1 electron. If I have 2 that are each going from -1 to 0, that's going to involve the loss of 2 electrons. Okay, and then if I look at reduction, Cr has that 2 there that I'm going to have to include. So Cr2 each have a +6 oxidation number. Okay, that is going to Cr +3. Okay, I'm going to first balance out the atoms here, so I'm going to have to balance this out by putting a 2 in front of Cr. Now each Cr ion going from +6 to +3 would be 3 electrons. So if I have 2 going from +6 to +3, that is going to be 6 electrons. Okay, so that was the first big thing I wanted to show you, is just you do have to take into account their subscripts here. It's really important. Okay, then from there I'm going to balance out my electrons, making sure that the number of electrons lost is equal to the number of electrons gained. That means I'm going to have to multiply the oxidation half reaction by 3, and the bottom one would just get multiplied by 1. And then I'm going to rewrite them over here. So 6 I -1, 3 I2, plus these 6 electrons, and then trying to line up those arrows, I have Cr2, my +6 plus my 6 electrons is yielding to my Cr +3s. Okay, then I can cross out my electrons that are lost and then gained, and then combine them below to get my net redox reaction. All right, now if we go through this one, we're going to see another exception that I wanted to point out to you. So if I look at my Cr2 +6, okay, this one here, which again, keep in mind this would be 1s there. Okay, I only have one spot where that Cr2 with a +6 charge is up here. Okay, so that means I can take that 1, and that is set in stone. That is going to be 1, as long as I did all my work correct leading up to that point. If I look at where I have my iodine with a -1 oxidation number, it is in multiple places, which means this coefficient is not going to go anywhere. Okay, so you have to leave that one out. That was the other big thing I wanted to show you. Then as we go and move along, I do only have one spot where the I2 is with a 0 oxidation number. That's up here, so I'm going to fill in my 3 there, and I do want to underline that so that I know that's set in stone, especially when you're going back and forth and balancing. That's really important. And then down here, I have my 2 Cr plus 3s. Okay, I only have one spot where Cr has that oxidation number. Okay, so I'm going to fill in a 2 up there. Okay, so again, a couple of different things with number 5 that I wanted you to see, but that gave us 3 of our coefficients. Those guys are locked in stone based on that transfer of electrons during the redox reaction. And then from there, you're going to go ahead and balance it. You might actually want to pause the video here and try this out for yourself. You'll end up seeing that you're going to need 14 in front of HI, a 2 in front of NaI, and then a 7 in front of H2O. Okay, so try out 2, 3, and 4, and then you will be all set. Great job.